Okay, so let's talk about hypothesis testing. Well, we're going to start out here talking about confidence intervals again, because confidence intervals are going to be the basis for what we're going to call hypothesis testing. Hypothesis is that we're going to put together a theory, a hypothesis that there's a difference between two groups or three groups or four groups, right? That, for instance, an intervention that we're going to do is going to have some beneficial effect. That a drug we're going to give a patient is going to have an improvement in their health. That an exposure causes a disease, that kind of stuff. So we want to be able to prove that kind of stuff. So we're going to start out by stating that as a hypothesis. And mostly in statistics, we describe that as comparing one group to another. In other words, for instance, if we're talking about something numerical like blood pressure, we're going to test a blood pressure medication or something like that. We're going to talk about the average blood pressure for people that, say, take a placebo versus the average blood pressure for people that take the blood pressure medication. Now, notice that with any medication, with any behavioral or medical kind of determination that we're going to make, there's going to be a variety of responses to a drug or a placebo. So we really can't just look at individuals per se in terms of what the response is. We really have to look at groups of people. And the easiest way for us to determine whether or not there's a difference between two groups is to compare the averages of those two groups, the midpoint of those two groups, and the variability within those two groups, because that tells us a lot about each of the two groups. So the idea here is that, for instance, if really the drug has no effect, it has the same effect as the placebo, then when I measure blood pressures, I'm going to be sampling from one big population with no differences between the two of them. It's really just one population, right? But if the drug does have an effect, then I have two populations. One population of people that took the drug with their own average and standard deviation, and one population of people that didn't take the drug with their own average and population. So whenever I take a measurement, whenever I take a sample of, say, 50 people, give them the placebo, 50 people, give them the drug, whenever I do that, there's a certain variability to what my results are going to be. Okay, so if I take people with the placebo, well, maybe my average with the first 50 people is blood pressure of 98, right? And then I take 50 people, same circumstances, same basic age group, same BMI, same ethnicity, and so on and so forth. And I take another 50 from that same group. I'm not going to get exactly the same number for the mean. I'm going to get a different number, right? Well, if I compare that to what might happen when I take a mean of people that took the drug versus these two groups that took the placebo, I'm going to get a different number for the people that took the drug. Well, there's two things going on there. One difference in the two means is just due to the variability in the population. In other words, I'm never going to get the same answer, exactly the same answer twice, but they are part of that same population. They both took the placebo. The average for the whole population is a certain number, but just by chance, one time when I take a sample, I might get one number. Second time, I might get a higher or lower number than that. But it's unlikely I'm going to get the same. So I can't just depend on the two means being different to say that the drug worked, right? So in other words, if I take 50 people that took the placebo and their blood pressure was 100, and 50 people that took the drug and their blood pressure was 95, I can say to myself, well, it looks like the drug is working. However, I might have gotten the same result just taking the same population and doing it twice with the same population. So how far apart do my two means have to be in order for me to say with a certain level of certainty that those two means are different because the two means of the populations I'm taking them from are different? Or perhaps that the differences aren't great enough. I can't really say that. Could have been just either one of those populations and just differences due to chance. So that's our real objective here. Being able to say with a known level of probability whether the means of two groups are really different or if the differences are really just due to sampling chance and they're really basically the same. The two populations have the same blood pressures. So, how do I do that? Well, I start with a hypothesis. I start by saying to myself, let's start off by saying that the two populations are not different. The two populations are the same. So now the onus is on me to prove, given that with a certain level of certainty, that they're different. So we call that in statistics a null hypothesis and an alternate hypothesis. Null means no difference or zero, right? So we're going to start always, almost virtually always, when we do a statistical analysis, with the assumption that there's no difference between the two groups that we're comparing. Later on, we're going to get into more groups and different kinds of variables and stuff like that. But for right now, we're dealing with numerical variables. So my null hypothesis is going to be always that the mean of group A is equal to the mean of group B. The mean of people that took placebo, the mean blood pressure is equal to the mean blood pressure of people that took the drug. And then from that point, it's up to me to do the sampling, find my statistics, find my mean, my standard deviation, and then to compare the two groups. We're going to get into some exercises doing that. For today, we're going to, you remember we mentioned that the T distribution was based on the work of this guy who used the pseudonym student, right? So we use the student's T-test. The student's T-test is useful there. So for instance, we started to talk about determining what the 95% confidence interval for a particular population, sample from a particular population is for predicting what the true mean is of that population. Okay. Well, for starters, we're going to look at that another way. We're now going to use that confidence interval, or the way that confidence interval is calculated, and we're going to compare it to a mean from a different population. We're going to call that a T-test. Okay, so our first kind of hypothesis test is going to be something called a T-test. Okay, and in this T-test that we're going to start with, for now, we're going to assume that we know, and this is just the way we're going to start to learn about this stuff, we're going to assume that we know the true mean for population A, say the people that took the placebo, or the general population, and we're going to compare that to a sample of people that we give the drug to. So we're going to call that a one sample T-test, because we're going to say mean one we know, but mean two we don't know, but we're going to calculate a confidence interval for it. So you might say to yourself, okay, you calculate a confidence interval for group B, the people that took the drug, and that confidence interval says that we're 95% sure that the mean blood pressure for people that took the drug is 90 to 100, somewhere between 90 and 100. Well, if the people that didn't take the drug, right, the average of the population that didn't take the drug, which we know for the whole population, everybody else, right, we've tested everybody else. If we know that that mean is, say, 102, or if that mean is 88, we can say with 95% certainty it's outside of the range which we're assuming that the group B is, the one that we're guessing at from the sample. So we can say that they're different with 95% certainty, right? But if the mean of the population that we're comparing it to is 93, well, that's within our confidence interval. It could be 93. We can't really say it's different than 93. So another way of putting that is that if you know with 95% certainty that you're going to collect 10 pounds of Halloween candy tomorrow night, right? Okay, but you know last year that you only collected 95%. You could collect between 10 and 20 pounds, let's say, and last year you only collected 8. You know that you're going to collect more. You're 95% sure you're going to collect more candy tonight, right, or tomorrow night, right? Where if last year you had collected 12 pounds, and this year you're 95% sure you're going to collect between 10 and 20 pounds, well, now you're not 95% sure you're going to collect more. because you might collect 11 or 10 pounds, which was less than last year, which was 10. So we're gonna start with that kind of assumption that we know one populations mean, but we don't know the other. We have to use the confidence interval, and we're gonna call that a one sample t-test. So I'm gonna back up and go through this PowerPoint, but I just want to introduce that idea to you because we're going to be using this idea of hypothesis testing and comparing means, and starting with the assumption that two means are equal or two proportions are equal, and then forcing ourselves to prove that they're different. And that's really what a lot of statistics is all about. Okay, so let me just start this PowerPoint. Okay, so we're also going to talk about error types and how they relate to confidence intervals and so on. Okay, so confidence intervals. We know what they mean now, right? They are, we're defining a range within which we have a certain level of certainty that the true mean for a population, numerical variable, true mean of a numerical variable for a population lies. Where, since we only know the mean from sampling, we never know what the population is for sure, but at least with confidence intervals, we know that within this range, we're 95% sure we've captured the true population mean, or within this range, we've captured 99% certainty that we've captured the true population mean. Okay, so it's a range of values within which we expect that to happen. Okay, so now we're not going to do the age survey. Well, maybe we can do the age survey. Let's see. Okay, tell you what. There's no easy way for me to do this without like having you write down stuff on paper. Okay, let's say I asked you to guess my age, right? Okay, now if I asked you to guess if your grade depended on guessing my age with 95% confidence, right, versus 50% confidence, right, which of those two ranges would be wider? The big one, 95%, right? Because if you want to be 95% certain you guess my age, you'd guess like, if you want to be 100%, you'd guess 0 to 200, right? But, that's only because that's the range of possible values. But if you want to be 95% certain, you'd guess a wider range. If you were willing to be only 50% certain, you'd guess could afford to guess a narrower range because you're willing to be wrong half of the time. Okay. Okay, so we learned that we calculate the confidence interval by taking a sample, taking the average of that sample, X bar represents the mean of that sample, right? And then we calculate a margin of error, how much we should subtract from that mean that we got from the sample mean, right? Because sample mean represents what we think the population mean is, but we're not really sure how accurately we know it at that stage. So we have a sample mean, and we're going to add and subtract the margin of error from that sample mean. And that's going to be our confidence interval. And the thing that determines how big that margin of error has to be is two things. Number one, what level of confidence that we want that we captured the real mean. That's going to be represented by the t-score or the z-score. Right? So when we know the population standard deviation, which is rarely, we use the z-score. If we don't know the population standard deviation, we use the t-score because we're gonna base our guess of the population standard deviation on the sample standard deviation, right? So we introduce a little bit more error. So we use the t-score times a representative of the variability that we would expect from samples of that size. So what is this saying? It's saying that that margin of error is based on two things. One thing is how variable the individual numbers are, the standard deviation, and the sample size. And the other thing is how certain we want to be that we're going to capture the mean. In other words, the t value or z value. Okay, so that's where we get that x bar plus or minus the t-score times the standard deviation of the sample, because usually we don't know the population, divided by the square root of n. One is called the standard error, and the other one's just called the t-score that's appropriate for that value. Okay? So now, when we use a t-score that's appropriate for, say, a 95% confidence interval, that means that we're willing to accept a 5% chance of being wrong if we miss if the population mean turns out to be outside of that range. Okay, but think about what happens then. If I have a null hypothesis, an alternative hypothesis, that leads to the possibility that I might say that there's a difference when there is no difference, right? In other words, I might take my null hypothesis, which is that the two means are equal, and say, well, it's outside the confidence interval, right? And say to myself, that these two means have to be different. Two population means have to be different. And at that 95% confidence level, that I know what the mean in the sample is, that means I have 5% chance of being wrong. The probability of my being wrong and rejecting the null hypothesis, saying that there is a difference when there isn't a difference, that's called the alpha error. Okay, and there's another kind of error called a beta error. Sometimes called a type 1 error also. Okay, it's called the alpha error or type 1 error. So if you're 99% confident, that's a 1%. Alpha is 1%. Okay, if you're 90% confidence level, that means that alpha is 10%. Okay, so there's another kind of error that you can have. Now, let's say that we say that the two means are different, and we calculate. Remember, I'm going to start with knowing one mean and one population. The confidence, we calculate the confidence interval. Maybe it's a small sample, right? Small sample means a bigger standard error. So it's going to be, that confidence interval is going to be pretty wide. And if it turns out that my mean from that other population falls within the confidence interval, I say that, gee, I can't reject the null hypothesis. I can't say that the means of the two populations are different, and they are in fact different, right? But you missed it because it was too small a sample. You weren't able to reject the null hypothesis, but in fact it really is true there is a difference between the two groups. That's called a beta or a type 2 error. So as we move forward, you're going to hear those terms every once in a while, and we're going to actually figure out how to calculate those things. Okay, so next thing, t-table. We got a pretty good look at the t-table from a couple of examples that we've been working on. We're going to work on a lot more of that today. Okay, so in this t-table, one of the things you may note is that for the 95% confidence interval, right, you'll see it, let's see, one tail, two tails. I'm going to look at this right in the middle here. It says two tails, right, 0.05. Okay, so I'm going to go down to the bottom here, and they don't give you the whole table, unfortunately. Okay, so a 95% confidence interval would represent this middle column here. Okay, and probably recognize these numbers. So if you go down to 30 degrees of freedom, it's starting to get pretty close to 1.96. They didn't put that last row that we have on our table. The infinity symbol shows 1.96, but we can tell this is a 95% confidence interval. Now notice that that means we have 5% chance of being wrong, which means that there's 5% chance that's split up between the two tails of this distribution. Okay, and each one of those sides each tail is 2.5%. So there's 2.5% chance we can miss on the low side, and 2.5% chance we could miss on the high side. Remember that when I mentioned that null and alternative hypothesis, I said the mean 1 is equal to mean 2, or we reject the null hypothesis, mean 1 is not equal to mean 2. Did I mention anything about which one's bigger? No, could be mean 2 could be bigger than mean 1, or vice versa. So most of the time we're doing something called a two-tailed test. We're simply saying that we're starting with one hypothesis, that the null hypothesis, that they're equal, and then the alternative hypothesis that they're not equal. That's called a two-tailed test. Okay, we're going to get, I don't want to introduce it right now, but it may come up in another slide, but we may be interested in looking at the possibility of, well, what if we know it could only go one way, it could only be bigger, it could only be smaller? That's called a one-tailed test. we're only going to test whether mean 2 is bigger than mean 1, not just different, but just bigger. We'll work out how that's going to help us or hurt us later on. Okay, basically allows us to make a determination, yes or no. Are these two equal or not equal? Are these two groups equal or not equal? Problem with that is whenever in statistics we say yes or no, it's always got an asterisk on it. It's always got a level of certainty or confidence. Okay, so whenever I say, oh, lead paint in an apartment is associated with higher lead levels in children, well, yeah, I'm 99% sure that's true. Now, I could be 99.9% sure that it's true if I took a bigger sample and compared more children that didn't live in apartments with lead paint and compare them to more children that did live in apartments with more paint. But my sample size always limits how certain I can be about making that yes or no or true or false statement. The only way I can be 100% certain that I'm right when I say that there is an association, for instance, is if I sample everybody, if I know the whole population. So anytime we're working in statistics, we're going to say, oh, there's a statistically significant difference between these two groups, right? But that's different than saying we know for sure. Okay, but because we're stuck with this. We're stuck with the kind of a situation where we can never know. We can never sample everybody or everyone's reaction to something or everyone's exposure to something. We're stuck with that some level of uncertainty. But the good thing is that we can quantify that level of uncertainty. We can know how uncertain that we are likely to be. Now, in most statistical studies, they're happy to get less than a 5% chance of being wrong, having an alpha error less than 5%. In other words, being at least 95% sure that they're right. Okay, that also tells you that, like, gee, a lot of studies get published. There's a 5% chance that their conclusion is wrong, right? So, in a lot of these, we're going to take a look at one in a second here. But a lot of these studies, it's up to you to interpret what these likelihoods of being wrong when they make various conclusions and so on. So let's read this. Proving that school-age children can yield substantial benefits, cognitive development. There's a limited experimental evidence of benefits of alternate school-based malaria interventions, or how the impacts of interventions varying according to the intensity of malaria transmission. We investigated, this is an abstract from an actual study. We investigated the effect of intermittent screening and treatment for malaria on health and education of school children in an area of low to moderate malaria transmission. Okay, cluster randomized trial. I think we talked about different trials. Clustered is one type of trial, right? Like, in other words, they might take samples from this group. They might take 5 children from this group. This group's bigger, so they might take 7 children from there, and so on and so forth. They broke it into clusters that they wanted to make sure they representatively sampled all these different groups. Maybe they were different tribes, maybe they were different cultural groups, maybe they were different areas where there was different levels of malaria transmission. Okay, but it was a cluster. Within each group cluster, they took a random sample. In Kenya in 2010 to 2012, the intervention was delivered to children randomly selected from classes 1 through 5 who were followed up for 24 months. Once school term, now it might be a public health kind of intervention, like teaching them about mosquito screens and so on and so forth, or it may have been some other public health intervention. Once the school term, children were screened by public health workers using a malaria rapid diagnostic test, and children with or without malaria symptoms were found to be RDT positive, were treated with the 6-dose regimen of a drug. Given the nature of the intervention, the trial was not blinded because they had to know whether or not they were positive. The primary outcomes were anemia and sustained attention. Secondary outcomes were malaria, parasitemia, and educational achievement. Data were analyzed on an intention to treat basis. During the intervention period, an average of 83% of the children in intervention schools were screened at each round, of whom 17.5 were positive, 80% and 80% of the children in control and 80% in the intervention group were followed up at 24 months. No impact was observed for prevalence of anemia at 12 or 24 months. Risk ratio 1.03. Risk ratio is a comparison of the rates of the children that were exposed versus the ones that were in the control group. So in other words, if you have a risk ratio of 1, it means that there's no difference in the risk for the two groups of children. So 1.03 is there's a little bit greater risk in the observed group, right? But the confidence interval included 1, which says basically you can't say with 95% certainty that it's different than 1. Okay, now notice P is equal to 0.621. P is the actual calculation of the probability of being wrong if you reject the null hypothesis. In other words, P, if the number had been 1.14 or 0.92, it would be outside of that 95% confidence interval, then P would have been less than 5%. You would have less than 5% chance of being wrong if you said that the intervention made a difference. Okay, okay, and so forth. Let's see if I can get the no effect of the 24 months. So I'll leave it at that for now. We'll come back to this at the end of the session and see if we understand a little bit more about this. Of being wrong, right? Okay, so like in other words, P is the probability that you would have gotten that outcome if there were no difference between the two groups. Okay, 60% chance, 62% chance that you would have gotten such an outcome if there's no difference between the two groups. So you want that to be less than 5% chance of there being no difference before you reject the null hypothesis. P is in Peter, yes. P is in percentage, right? Percentile or percentage. Okay, or proportion. Okay, okay. Let's see. Okay, so now this is kind of another way of looking at it also. If you have a bag of beans, right? You can't look into the bag of beans. Could be white beans, could be brown beans, right? So if you reach in there, pull out a handful of beans, and there's only a few white beans in them, right? You would come to the conclusion that most beans in that bag are not white. Only a few of the beans are white. You would think that that most of the beans there were brown. Now, if you did the same thing and you had another bag that you thought was all white beans, but you did the same thing, you would think that it came from a bag that was different as well. Okay, kind of a lame way of describing this. Okay, okay. So now, as far as the alpha and beta error is concerned, for the most part, alpha errors are more problematic than beta errors are. Okay, what happens when you have an alpha error? When you have an alpha error, you're saying that this drug worked, that there's a difference between the placebo group and, when you reject the null hypothesis, you're saying that group A is different than group B, the means are different. So you're saying that the intervention or the drug or whatever else it was made the two groups different. And you would recommend some action based on that, right? So now, if you are wrong about that, that's called an alpha error. That's a bad thing, right? Because what happens is then you have proposed a hypothesis and proven a hypothesis, presumably with that level of certainty. You've proven that this should work, and now people are going to spend money on it. There's going to be interventions. There may be risks to it if it's a medical intervention, and so on and so forth. So alpha errors are bad, right? Beta errors are when there is a difference between the two groups, but you fail to prove it. Okay, and most of the time a beta error is not as critical as an alpha error, because a beta error, for instance, let's say that the difference, the mean for group A is 10, mean for group B is 15, but your confidence intervals are such that you just barely can't say that they're different. In other words, just overlap just a little bit, right? Well, you can then go back and you can do a study again with a larger sample size, right? Or define the study a little bit better, right? Most usually it means going back with a larger sample size. So, but you're not proposing an intervention based on the results of that study. Okay, so it's unfortunate, but a beta error when there is a difference between two groups, but you fail to identify it, that's not as bad as identifying a different that's not really there. The analogy that they use in a lot of statistics class is a courtroom, right? So courtroom, you're presumed innocent until you're presumed innocent unless you're proved guilty, right? So an alpha error in that case is an innocent person that's found guilty, right? So that's not as bad as a beta error, which in a court would be if there's a guilty person that he winds up not being found guilty. Okay, that's the opposite. Okay, beta would be when you don't find a difference when there is one. Okay, which you can always recover from. A little harder to recover from an alpha error. Yeah, we'll see that as we move on. It'll be a little bit clearer. When we work on examples, real life examples, it'll get a little bit clearer. What's that? That's also a type 2 error. Beta error is also called a type 2 error. Okay? And remember, again, we talk about two null hypotheses. In the case of the defendant, finding the defendant guilty, right? Is first of all, the null hypothesis is that he's innocent. The alternative hypothesis is that he's not innocent or guilty, right? So if we, in order to reject the null hypothesis and prove him guilty, we need some level of certainty, right? Okay. Okay, confidence.
Alpha error is what? So the beta is no difference when there is a difference. The alpha error shows.
Well, alpha error is the alpha error is just the probability that you make a mistake and say that two means are different when it turns out when in real life the means of the populations are not different. Right? The means of the samples are always going to be different. Question is, are the means of the population they came from really different? Okay, so one of the ways that we can look at this is to compare the mean of a sample that we take to the mean of a known population. Remember that single sample t-test I was talking about? So I can say that, gee, the mean of the sample, let's say the mean of the sample is 100, right? But I'm comparing it to a population when the mean is 90. Okay. So what I can do is I can say to myself, I'm going to assume for a moment that maybe that sample mean is correct, that's the true mean of that particular that population that the sample that came from. What's the probability that you would get a value that's so different from that one that they would be 10 apart? In other words, the sample mean came out to be 100. You're comparing it to a number 90. What's the probability that we would get that big a difference, 10, right? If we were taking a sample of that size, right? In other words, are those two numbers 2 standard deviations apart or 1.96 standard deviations apart? So really kind of what we're doing is we're going a little bit backwards and we're trying to see whether the difference between the two numbers, the mean of the population and the mean of a sample that we took from a different population that we think is a different population, whether they're so far apart that we would expect that difference, that sample, to come from that population less than 5% of the time. In other words, be so different it would only come very rarely or relatively rarely. Okay, so what are the steps we're going to use? Number one, we're going to state the hypothesis. Mu1 is equal to this. And the hypothesis is always going to be stated with the population parameter. Okay, in other words, we're not interested in whether mean of group one, the mean of sample from group one is equal to the mean of sample from group two, because they're always going to be different anyway, even if they came from the same population. Always going to be a little bit different. Okay, what we want to know is whether the mean of the two populations are different. So when we say the hypothesis, we're always going to state it from the perspective of the population parameter. In other words, mu1 is equal to mu2. Then we're going to say to ourselves, what level of certainty are we interested in? 95% certainty, 99% certainty, 90% certainty. And we're going to state that in terms of the level of error we're willing to accept, alpha. So if alpha is less than 5, if we're 95% certainty, we're going to set alpha at 5%. Okay. And then we're going to take our sample. We're going to calculate our standard deviation from that sample. We're gonna determine what sample size we want to use, and then we're gonna calculate when we take the mean of the samples. We're gonna look at the difference between the two means, and we're gonna determine whether those two means are so different that they would exceed the level that the two standard deviations or 1.96 standard deviations if we're setting alpha at 5%, 95% confidence. Well, that's one way we could look at it, right? But since we're using statistical tools, calculators, and so on and so forth, we can also use it a little bit differently. I'm going to sketch this out later on, so it makes a little bit more sense. Since we know that since we determine from our sample an approximation of the population standard deviation, we know the sample size, we know our standard error, right? And we can actually determine how many standard errors apart these two numbers are. So if they're two standard deviations apart, we know that that would happen less than 5% of the time. If they're three standard deviations apart, we know that that will happen less than 0.1% of the time, 0.3, because 99.7. If they're only one standard deviation apart, well, that could happen. You could have 16% of the time, you could have two means from the same population that are 16% of the time, one is lower than the other, or 16% of the time it could be higher than the other. Remember one standard deviation, right? That 16% of the time, we could draw two samples of the same size from the same population and get results that are 16% of the time lower, 60% of the time higher. We could get 32% of the time, we could get values that are 1%, one standard deviation apart, or one standard error apart, right? Because that's just the way that the normal distribution works. Right? Now, two standard deviations apart, that gets less likely. That only happens 5% of the time, right? Well, in fact, we don't have to be limited to whole numbers of the standard deviation. We could actually calculate for any particular difference between two calculated means, two sample means. We could calculate how many, based on the variability, the standard error, we can calculate exactly what the z-score is or the t-score is for those two differences, for that difference. And if we know the t-score, we know how much of the normal distribution is left outside of that. So we could literally state the probability of getting that big a difference, not just by saying that it's greater than 95% or greater than 99%. We could also actually pin an exact percentage on it by looking it up in the Z table or the T table, right? So in other words, I could compare two values. I could say the null hypothesis is mu1 is equal to mu2. And then I could do my samples, take 25 people from this group, 25 people from this group, compare the difference of the two means, calculate my standard error, and say, well, these two numbers are 1.74 standard deviations apart. In other words, the t value or z value is 1.74. I could predict what the probability is of getting that extreme of value as a percentage, as a p-value. So if I want to be 95% certain, I want that p-value to be so far apart that it'll only happen less than 5% of the time. So a p-value less than 5% is what I'm after. Number of standard deviations apart more than 1.96, or a p-value less than. So in other words, if they're 2.5 standard deviations apart, my p-value might be, instead of being just less than 5%, I might be able to say it's less than 2%, right? Because of the way the standard deviation works. When we see this on paper, it'll make more sense. That's the difference between using the p-value and just stating whether it's inside or outside of the confidence interval. Okay. Looking at this on PowerPoints, discussing this from PowerPoints, is a lot less intuitive than actually doing it and playing around with the numbers. It'll make more sense to you once we start working with it. Okay, null hypothesis. No difference between the two values. Sample, it presumes that a sample is drawn from a random, it's a random sample, that they're independent, two groups are independent. And if true, then any difference between samples that are taken between the two groups is just due to chance. Okay, if the null hypothesis is true, any difference between the sample mean that you get from group A and the sample group that you get from group B, if the two means are different for the are same for the two populations, any difference is just due to sampling error, just sampling chance. The alternative hypothesis, that states that there's a real difference, that mu1 is not equal to mu2. And if indeed that it's true, then the difference is not due to chance. The difference is big enough that we can say with a certain level of certainty that it's real and not due to chance. So usually we're in a situation where the wider the differences between the two means from the two samples we take, the more likely that they're taken from populations that really have different means. Okay, I'm kind of restating the same thing a lot of different ways. Okay, here we are. It's outlined here. So null hypothesis for a two-sided test, alpha is equal to 0.05. Null hypothesis, H0, a lot of times, or H null. Mu is equal to mu0. Alternative hypothesis, mu for the population we know is not equal to mu0. Example, blood pressure of smoking males is the same as the general population. Okay, so what we're saying is that for the general population, the blood pressure of everybody in the general population. Okay, I guess you could argue that we have a pretty good handle on that. Insurance companies, they record all this. You could probably go to all the insurance companies, gather all the information, and you could say that blood pressure is, it's obviously it's not blood pressure. I guess cholesterol, whatever this is. 200, it's obviously not blood pressure. The mean cholesterol is 211 milligrams per deciliter, right? Our alternative hypothesis is that the mean for smokers is not equal to 211. Notice all they did there was substitute the known value, right? Mu equals a mu for smokers is equal to mu for the entire population. That's what mu0 represents, the entire population. So a mu for smokers does not equal the mean for the entire population. Alternative hypothesis. They restated it down below that because it's comparing it to, since we know the population, general population cholesterol level, we're saying that a null hypothesis is that there's no difference between the general population and the mean for smokers. So mu for smokers is equal to 211, same as the general population. The alternative hypothesis, mu for smokers is not equal to 211. It's either greater than or less than 211. Okay, so that's a two-sided hypothesis, but we're only taking one sample. It's a single sample t-test. Okay, we're starting with a value that we know, taking a sample from another group, and seeing how it compares to that first group. Okay, so now the second one is that we're taking two samples. This is a two-sample t-test. Mu of group 1 is equal to mu of group 2. The mean of population 1 is equal to the mean of population group 2. And so we're saying that the alternative hypothesis is that they're not equal. So there's another way to state that. Sometimes you see that stated as the difference between the two means of the populations is equal to 0. Basically, it's saying the same thing. I don't like that. That's a little bit confusing. So I prefer the way it's stated in the beginning, but you could state it that way as well. Okay, and the null hypothesis would be mu1 minus mu. That would be the null hypothesis that mu1. They did a little bit of an error there, right? Mu1 minus mu2 is equal to 0 is the null hypothesis, and the alternative hypothesis is that there's a difference. Mu1 minus mu2 is not equal to 0. So that's a typo there. That shouldn't be there.
Wait, the typo is the not.
Yeah, it's not. That should say not equal to 0, right? Everybody agree with that? Right? Mu1 minus mu2 is not equal to 0 because if they're different, then when you subtract one from the other, it's not going to be 0. Okay, if they're the same, it's going to be 0. Okay. Yes?
Going back, what's the difference between this, the way this is stated, versus the previous slide?
The previous one is a single sample.
Mine said not equal to 0.
Yours says not equal? What's mine say behind me?
Equal.
Look at that. Okay. I must have corrected on one of them and not on the other. Okay. Yeah, mine's different than yours. Yeah. It must be two versions of this file. Yeah. That's like, I correct some versions of it, and then there's the original version still floating around. So I must have opened the old version. Okay, so at any rate, you were saying, I'm sorry. Okay, in this one, one of these two means we know for sure. The population mean we know is 211, right? That's not a sample. We're not taking a sample. We know it's 211. The only thing we're sampling is we're taking a sample of, say, 100 smokers. So mu is the mean for smokers. Mu 0 is the known value for the entire population. So there's only one sample involved. So we could state it as mu for smokers is equal to 211, or mu for smokers is not equal to 211. Because we know one of the two values. There's only one sample involved. This one, there's two samples involved. Population 1, population 2. We take a sample from population 1, take a sample from population 2, and we compare the two means. This is more common than the single sample one. Single sample one's going to be easier for us to calculate. That's where we're starting with it. But in real life, most of the time you take two samples. Okay, so one of the things when you take two samples, okay, sounds okay, right? The difference, you take a sample from group 1, you get X bar 1. Take a sample from group 2, you get X bar 2. Okay, now you want to calculate how many standard deviations apart they are, right? Can you see a problem here in terms of calculating the standard deviations? Well, over here you only got one group, one sample. Calculating the standard deviation is easy. You only got one group of numbers. Calculate standard deviation. How about here? Now you took two samples. Which standard deviation do you use? Use the one for group 1 or group 2? Can you combine the two of them together to get the standard deviation? Are they different? Is one big and one variability in one group bigger than the variability in the other group? It gets complicated when you're working with two groups, the standard deviation part. That's why we're going to start with just one sample. Okay, that's going to come up. Now, there is another way to look at that also. Most of the time, statisticians will work with two-sided hypothesis. In other words, you're willing to say that the null hypothesis is mu1 equals mu2, and the alternative hypothesis is that they're the difference. In other words, not prejudging what the difference is, whether the second group is more than the first group or less than the second group. Okay, it is possible to have a situation where you may know that it can only go one direction. Okay, so now where would that happen? Like, for instance, let's say that you were testing a blood pressure drug, which is a vasodilator, right? If it's a vasodilator, you might make the assumption The only thing that's possible, because of the mechanism that it works on, the only thing that's possible is whether or not it lowers blood pressure. It can increase blood pressure just simply because of the way it works. You might be willing to then set up a one-sided alternative hypothesis. In other words, you might be willing to say mu1 is equal to or less than mu2, and then the alternative hypothesis, only that one is greater than the other. In other words, predict ahead of time one is greater than the other. That's one-sided. You're only going to prove that one is greater than the other. Well, why is that? Why would you want to do that? That's a less rigorous test. The reason why it's a less rigorous test is because you're only looking at the possibility that they're far enough apart to be in the upper or lower 5% of the normal distribution. If you want to predict, if you're not going to pre-predict whether one's lower than the other or vice versa, well then you have to split up that 5% between the bottom and the top tail, which makes it 2.5% on either side. So you have to be further away to be outside of that range so you can reject the null hypothesis. If you're willing to put all that 5% on one side, then you don't have to be that far away from each other, as far away from each other. So a one-sided alternative hypothesis is a less rigorous test than a two-sided. So in many statistical studies, they, even if they have the opportunity to, and they could justify it, which not all that easy to justify, they probably would stick with a two-sided hypothesis. Most of the time, maybe occasionally, I might give you a word problem that involves a one-sided hypothesis, but for the most part, I'm going to try and stick to two-sided hypotheses, equals or not equals. It demonstrates everything that we needed to demonstrate without adding the extra confusion. Whoops. Let me go back. Okay, there we go. Okay, choice. Okay, it's controversial. Like it says here, it's controversial because the one-sided is it's going to require a smaller percentage. It allows for a larger percentage of the tail of the distribution of the normal distribution for you to use to demonstrate that you're outside that, far enough away from the other mean that you can reject the null hypothesis. So it's less rigorous. Who would want to use a one-sided test? Let's say you're Merck, and you want to prove that like that vasodilator I was talking about, you want to prove that it's effective at lowering blood pressure. Well, if you can use a one-sided test, it means you can have a smaller sample size and still demonstrate what you need to demonstrate. Okay, so you might be tempted to use a one-sided test. Okay. Alpha's revealed type 1 error and rejecting it. Okay. But number one thing you have to do is decide whether you're going to use a one-sided test versus a two-sided test. We're almost always going to use a two-sided test. Step number two is you're going to want to determine what your significance level is. In other words, it's kind of cheating to do the test, to do a sample, do the test, and then say, oh, I'm satisfied with 90% certainty. I'm going to use alpha's 10%, right, versus alpha's 5% or alpha's 1% if it's really critical, right? So you really should choose your level of significance that you want to use to prove a certain thing before you actually do the test. Alpha is usually 5%, 1%, or some value like that. Okay. Then the next thing you want to do is you want to calculate the test statistic. How many standard deviations apart are the two values? And if you look down here, you'll see they use the formula Z, okay, for a large sample. Right now, we don't know what's that. We calculated Z using this formula before. This is the number of standard errors or standard deviations apart. In this case, we're dealing with a one-sample t-test or z-test, where mu0, the population mean of one group, is known, but the population mean for the other one is not known, so we're using the sample mean. And it's assuming we also know the standard deviation and the sample size we choose, so we're always going to know that. Okay, so this is the way we calculated the z-score. Difference between the two means divided by the standard error. Okay, so now in this case, it's a one-sample t-test. and we know the standard deviation of the population. If we don't know the standard deviation of the population, this becomes a t-test instead. So we have to use a different distribution. Okay, and we use S, the standard deviation of the sample here instead. Okay, and the way we calculate it, the third thing is the next thing we do, step 3, is we calculate the test statistic. Okay, we calculate what the z value is. And the further apart, the bigger the z-score is, the difference between the mean of the population and the mean that you get for your sample, the further apart that they are, the less likely that they came from the same population. So if you get a z, if in the previous one we knew, I'm going to assume we know sigma as well as the mean of the population. If we know that, then we know that we have to be so far apart that the z-scores, the difference between the two means, have to be 2 standard errors apart, 1.96 standard errors apart, so that there's less than 2.5% there's less than 2.5% chance that the value that 2.5% chance that you would get this if they both came from the same population, okay, or 2.5% on the low end. In other words, the further apart they are in terms of z-score, the less likely you would get that if they were part of the same population. So that z-score represents the probability that you would be wrong. You would be wrong if you reject the null hypothesis that they really are part of the same population. So in other words, if we got a z-score value of 1, this looks like about 1, got a z-score value of 1, well, that means that 16% of the time we could take a sample from this population, this known population, 16% of the time we could take a sample of that size from this population that would be higher, more than 1 standard deviation away from the true population mean. So we would have 16% chance of being wrong if we reject the null hypothesis that they came from the same population. Okay, if we were 2 standard deviations apart, then we would only have 2.5% chance that we would be wrong and that they came from the same population. The further out you go, the less chance that that your sample came from this population. And the last step is you can actually calculate what the p-value is. In other words, if you know how far apart they are, you can actually calculate what that error is. If z is 2.04, you could actually calculate that this area here is, say, 2.3%. Now notice I said 2.3%, right? Well, 2.3%, you have to double that for a two-tailed test, right? Because we didn't pre-assume whether it was going to be higher or lower, so we'd have the same probability of getting that extreme of value on the low end too. So if it's 2.3% times 2 would be 4.6%. So that's still less than our tolerable level for error, which is 5%. Okay, so we calculate a p-value. In other words, instead of just looking at the confidence interval and whether it's in or out, we actually calculate a number called a p-value, and we're hoping for it to be less than 5%. Okay, and then once we've done that, we examine that p-value. If it's less than what our acceptable level of error is, in other words, if the p-value is less than alpha, if p is less than 5%, if that's what you say alpha for, then you can reject your null hypothesis and accept your alternative hypothesis. Okay, summary of the steps that we just went through. Okay, I'm going to go through some examples of our own. Okay, let's see. Okay, let's take a look at this. This is Levi's statistics here. We did a survey based on a survey we did when they had students guess our ages. So I don't want to get into that, however. So our null hypothesis is that they thought, I think the average that they guessed his age to be was 41.9 years old. Okay, and the idea here is he really, did they really capture his specific age. So apparently his real age was 38.5. Oh, I'm sorry, it's the opposite. His real age is 41.9. They guessed 38.5. That was the average of all the guesses. So the known value for his age is the actual value for his age is 41.9. So our hypothesis is that the mean for the sample that of our guesses is equal to his actual age, or it's not equal to his actual age. So we calculated the t-score for the difference between the average that the students guessed versus his real age over the standard error of the guesses. Right? There were 23 students guessed at it. There's the standard deviation for their guesses was 3.9, and the t-value came out to be -4. So in other words, that means that they underestimated his age by a t-score of 4 standard deviations. So 4 standard deviations is very unlikely, right? So in other words, if we look up, yes,
Ours is different. It was updated.
yeah, don't worry about it. You look at either one. I can't see yours. I can only see yours. Okay, so yeah, just keep an eye on mine over here for now. So that t-score, you can actually calculate whether that t-score exceeds the value that you need to be have the t-value that you need in order to reject the null hypothesis. So the t-score that you need to reject the null hypothesis for a sample size of 22, right, for an alpha error of 5%, if you look it up on the t-score, you need a t-score of 2.07 to represent a difference that's of 95% or outside of that 95%. The t-score itself came out to be 4.11, which means that you have even a smaller likelihood than 5% of being wrong if you reject the null hypothesis. So that's called a critical value of t. Well, when we get into some examples, it'll make a lot more sense to you. Okay. Take a random sample. Okay. How about this one? Is this one the same on yours? Cholesterol levels normally distributed with normally distributed with the mean being 211 and standard deviation for the population being 46. Do hypertensive male smokers have the same cholesterol? Null hypothesis is that there's no difference between the mean cholesterol for smokers and the general population, which we know the mean of. In other words, null is mu is equal to 211. Mu is equal to mu 0. Mu is equal to mu for the entire population. Alternative hypothesis, that the mean for smokers, mu, is that what you see behind me? Is that the same thing? Okay. Mu for smokers is not equal to 211. Okay, we're going to let alpha equal be 0.05. We want to have less than 5% chance of being wrong if we reject the null hypothesis. Okay, so we take a random sample of 25 smokers and find their average cholesterol. Okay, in first case, we're going to have 2 cases here. First case, we find that the average cholesterol is 195. We also, let's imagine if we did it again and found 227 to be the average cholesterol. Okay, so let's take that first one, that 195. How many standard errors apart is that 195 from the population mean that we know, 211? Okay, well, it's x bar minus mu, 195 minus 211, over the standard deviation of the population divided by the square root of the sample size. So the z-score is negative 1.74. Now, looking at that z-score is equal to negative 1.74, does it look like there's less than 5% chance that these are from the same population? Does it look like it's going to be likely I can reject my null hypothesis, which I would only normally do if the z-score is at least 2 standard deviations apart, 1.96 standard deviations apart. Doesn't look like it, right? Doesn't look like it would be that unlikely to get that big that size difference? Well, in fact, the probability of getting this outcome, you could go to the z table. The probability for getting a value below 1.74 is 4%. So the probability, you're going to double that because you want to include both tails. So the probability of getting that outcome, given that smokers are not different than the general population, is 8%, which is not enough to reject your null hypothesis, right? Got to be less than 5% chance of getting that value. Okay, so how about 227? Is that going to come out the same way? Well, 227 minus, that's 195 minus 211 is 16. 227 is also 16. It's going to come out to the same result, except that the z-score is going to, instead of being minus 1.74, it's going to be plus 1.74. We'll get some examples of this in later on. Okay, same thing works with proportions. Remember, we work with proportions. We can test the proportions of two groups, or a one sample and a population, the same way that we would with a numerical variable. Okay, z is equal to p cap, our proportion for our sample, minus p that's known. Remember, this is a one sample z-test over the standard error. And I'm using z when I'm working with proportions because I'm almost always working with large samples when I'm working with proportions. Okay, and the standard error, we saw how to calculate that from our confidence intervals. Okay, I'm gonna move on from this so that we can actually work on some examples, and it'll make some sense. I think it'll make a lot more sense to you. Okay, let's see. Let me go back to my. Okay. Part 1.